Well, let's get started. I think we're going to have some more people trickle in. But we're very happy to have Professor Floyd Williams come talk to us today. He got his bachelor's at Lincoln University, then later his master's and PhD at Washington University in St. Louis. He studies Lie theory, math physics, homological algebras, and quantum mechanics. And today he's going to talk to us about the number 8. Without further ado, Professor Williams.
Well, this is a special week. We have the privilege of Professor Adam Fox to come to UMass on Tuesday and speak to us. He gave a very beautiful lecture. So it's really great to reciprocate and to get this talk in. It's been postponed a couple times, but it's a great day to be here. Thank you for coming. I guess we could summarize the talk just by calling it 8. But we have a few more words to describe the lecture. And I'll give you an outline to begin with. The talk is really geared for undergraduate students trying to keep things elementary. We should talk about matrices and infinite series, essentially. I'll begin with positive definite matrices, and this is where the question of divisibility by 8 comes in. Then theta series, and a very special theta series called E8. And then how this series E8 is related to other standard Jacobi theta series, and also to a Klein delta invariant. And then how the number 8 comes up in the study of elementary particles, and a little bit more about the divisibility by 8, or at least near divisibility by 8, and then some closing remarks. Again, if you have any questions or comments, please feel free to interrupt me, and don't wait till the end of the lecture. Let's start with the definition of a positive definite matrix. So we'll be interested in real matrices that are symmetric. They coincide with their transpose, or Aij is Aji. And to such a matrix, or any matrix for that matter, you can assign this particular function. We call it f sub A, this matrix multiplication. And then it turns out that the following conditions are equivalent. If either one of these 3 conditions hold, we say the matrix is positive definite. Again, I'm assuming that it's symmetric to begin with. One condition is that the eigenvalues are positive. They're certainly real because A is symmetric, so they're real, so it makes sense to ask it to be positive. Another condition is that this associated function is positive definite, meaning that there should be 0, at least, positive non-zero vectors. And then the third condition is that it has a product representation for a suitable non-singular matrix, B. These 3 conditions are equivalent. And I say that the matrix is positive definite. Either of these 3 conditions holds. I'll give some examples in a minute. And since we'll need a certain statement later, let's just get that out of the way now. So here's Fa by definition, the sum over I and J. So let's split the sum up 3 ways, where I equals j, I is less than j, or I is greater j. And of course, we can interchange, this is double summation, interchange I and j to get this equation. And then use that A is symmetric to write it this way. So I'm saying that this term here is really the same as, the third term is really the same as the first term here, due to the symmetry of A. So I can write F this way for I equals j, and then twice the terms where I is less than j. Now later, I'm listed in the case where all of these entries in A are whole numbers. We say that A is an integral matrix. And then I'll write X this way as an n-tuple of integers. So by this formula, you see that F, the image of F is in the integers as well. Because the Aij's are integers by assumption, and so are the X's. But the point here is that if I assume that the diagonal elements are even, that's an assumption, then, let me see what I'm saying. Oh, yeah, okay, yeah, then this is an even number here. And then I multiply by 2 here, that's an even number. So actually, this function will take values in even integers. I'll come back to this point later on in the lecture. Any comments or remarks? So some examples of positive definite matrices. I guess I'm recalling what an eigenvalue means. And it's convenient to write this x and Rm also as a column vector. So you want A to act by a multiple of a non-zero vector. So that means that the kernel of A has to be, at least this difference has to be singular. Term has to be 0. So the simplest example possible is the diagonal, the unit matrix, I guess. And then the right output, this FA is just a sum of squares. It's certainly positive for the vector being non-zero. So this is a positive matrix. Second example, I compute eigenvalues. They turn out to be 1 and 3, they're positive. So this is a positive definite matrix. You can see it by also looking at this function f of a. Just do this algebraic manipulation to get a sum of squares. So this is 2 reasons that this matrix is positive definite. A third degree example, compute eigenvalues. They are positive. Square root of 2 is something like 1.141, so this is certainly positive. The second way to see that this matrix is positive definite is to look at f of a, with it ordered that way, but you eventually write it again as a sum of squares, and that would be positive if the vector is non-zero. And of course, the last example, simple example where this matrix is not positive definite because here's a negative eigenvalue. Remember, positive definite means that it's symmetric and the eigenvalues are positive. Also, you can check this function fa. It can be negative for the right choice of vector, 1 and minus 1 in this case.
Excuse me.
Yes.
You know, is there a way to just looking at the matrix to figure out what the sum of squares, if you're going to be able to get what the coefficients would be for it or anything?
You sort of kind of complete the squares, I guess.
Okay.
Yeah, you mean if it's
If there's a way to sort of start the matrix and you can sort of piece together, maybe knowing the eigenvalues or something would get you to, but I guess just completing the square would do the job then.
Yeah, but I even tried to do that for E8, which I'll show later. I couldn't do it in that case, so
I see.
it might be something a little bit more subtle.
Cool.
So here's the first appearance of the number 8, or at least built by 8. There's a theory by Herman Minkowski, who, by the way, was one of Einstein's teachers. And he didn't have too much good to say about Einstein. He said that Einstein, he said he doesn't know anything, nor will he ever know anything. But
It's all relative.
But he says take a symmetric, positive, definite matrix. That's what we're looking at. And we ask that the entries be integral and that the diagonal entries be even. That's the situation we had a minute ago. But we want the determinant to be 1. Maybe such a matrix does not exist in the universe. The condition that such an M by M matrix exists is that M be divisible by 8. That's not obvious at all. In fact, I'll remark that there seems to be no algebraic proof of this fact. The proof is complex analytic. It's like proving the fundamental theorem of algebra using Liouville's theorem. You know what I mean? You take the reciprocal of the polynomial, show that it's entire, it's bounded, therefore it's constant. But you can do that algebraically, but it's harder. So I'll come back to the question about the proof later. So I go back to example 3. It satisfies all the conditions, is positive definite, except the determinant is not equal to 1. And of course, this is no contradiction because 3 is not divisible by 8.
Right.
So let's enter E8. This matrix comes up in Lie theory, goes way back to Killing, when he classified he made a mistake. He tried to classify all his simple Lie algebras, made a couple of mistakes, but they were corrected by Cartan. But anyway, I think this is the first time E8 comes up. So here's the matrix here. We give it the name E8. It turns out to satisfy, I'll show you in a minute, eigenvalues, all of the conditions of Minkowski's theorem. And this is the 8-dimensional matrix, 8 by 8. And this is the first part of the title of the talk, 8 meets E8. Going back to Caleb's question, I tried to look at FA directly and write it as a sum of squares. I think it could be done, but I wouldn't be able to do it. So as a matter of fact, I just went to, well, I have just a remark here that, you know, this matrix comes up in string theory, gravity, quantum gravity. And this is what's called heterotic string theory that has E8 cross E8 as this gauge group. This is not a group, but there's a Lie group also called E8. So I looked at a Maple program, and we computed all of the eigenvalues of this matrix. These are they. And you can see that they're all positive. And they actually lie in the range from 0 to 4, they're bounded by 4. there's some general lead theory with regard to these are so-called part-time matrices. And if you take this, these 8 numbers here and multiply all these 8 numbers, you get 1. Not obvious. You have to. The product of the eigenvalues is the determinant. So this is the smallest, an example of the smallest matrix that can satisfy the Minkowski theorem. And as I said earlier, the proof of Minkowski's theorem depends on complex analytic properties of beta series. And an open problem is to find a linear algebraic proof, because the theorem is completely algebraic in nature. So I want to introduce beta functions, or beta series, motivated by a question: what whole numbers are a sum of squares of 2 whole numbers, or maybe 3 whole numbers, or maybe 4 or 10? And if you can write it as a sum of squares, how many ways can you do it? Obviously, it'd be a very complicated problem. Take the number 3. It's not a sum of squares, but 2 whole numbers. If you try to write 3 this way, where you had integers, then if you ignore, well, let's see, that would say that yeah, well, n1 squared would be less than equal to 3. And if you take the square root, n1 would be between square root of 3 less than equal to square root of 3. There's no whole number solutions there. I'll come back to some more examples. So let's go back to our A, which is a real symmetric matrix. And then we can form this so-called counting function on the non-negative integers. I look at n tuples, m tuples of integers, such that this function takes on the value of L, for L fixed. So let's look at some examples. Go back to the first example, the simplest one, after the sum of x squared plus y squared. And then the possibilities for the sum of squares to be 2 are given this way. The 4 possibilities, plus or minus 1 combinations. So this number here is 4. We'll go back to example 6. That's the one here. That's there are no solutions, so the answer is 0. Another example. Take L to be 5. How many pairs of integers will the sum of squares end up being 5? You can write all of them down here, the 8 possibilities. So this counting function at the value 5 is 8. So let's take m now to be 4. Take the diagonal matrix that's positive definite. Here's our f. Sum of squares is positive definite. The problem would be kind of hard, so we look at Jacobi's theorem in this case here. it computes A directly, in this case, I mean the counting number, it turns out to be a sum of positive divisors if L, if L is odd. If L is not, you multiply by 24. If L is even, you look at the odd positive divisors. So I'll give some more examples here that get these numbers can grow quite largely using Jacobi's theorem. In fact, it's impossible to compute these counting numbers, generally speaking. On the other hand, you can get some information by making them part of a theta series, making these things coefficients. So I want to take a fixed tau in the upper half plane. This will be the notation throughout the rest of the lecture. And then I form this so-called theta series. So you might think if you could get some asymptotics on this theta series using complex analytic methods, for example, it might give you some information about these counting numbers. And then you'd be solving a problem in number theory, what numbers are a sum of squares, for example. So I'll repeat Minkowski's theorem, the conditions, and then I'll repeat the definition of the counting numbers. And then using that information I had at the beginning of the lecture, we can sort out the terms, I'm sorry. Take L be 0, you get 1, and then I want to write it this way. Because these conditions at the beginning of the lecture, you're really summing over the even integers. So I'm writing the theta function this way. Now, the first important thing about these theta series is Jacobian inversion. This is periodicity. This is an easy periodicity condition because we have the exponent e to the z is 1 if known that z is 2 pi I times some energy. That's what this statement is. So that's not deep, but this is a lot deeper here. It's inversion because I'm relating, I take a point in the upper half plane. If I take the negative reciprocal, that point is also in the upper half plane. So I'm relating the two values here. That's why it's called inversion. So h is upper half plane, and tau is there in the upper half plane, and so is minus 1 over tau. And here we have a complicated square root, but this is in the case of E8 again, so this is going to simplify quite a bit. And Minkowski's, this Jacobian inversion theorem, which is really amounts to the Poisson summation formula. Namely that you have a suitable function, the sum of that function over the integers is the sum of its Fourier transform values with a suitable normalization of the Fourier transform. That's the Poisson summation formula. It's really a billion version of the Selberg trace formula if you really get wild about it. So, Jacobian version implies the Minkowski theorem. And that's what I said, let's try to find a proof that's completely algebraic. So let's go back to example 8 again. I'm just repeating the matrix that we had earlier. The smallest value for which Minkowski's theorem can hold. And of course, in this M here, this is like the square root, that's 1/2, and M is h, so you get a 4. So you Jacobi inverse and simplifies this way. Now, it turns out that these two conditions, this condition and this translation condition, are enough to show that this function is modular in the sense that if you take any matrix of integers, we call it SL2Z, integer coefficients where the determinant is 1, then this theta function would transform this way. In other words, this is what people call a modular form of weight 4. And in fact, you can show that the general theta series that I defined is a modular function of weight m over 2. So this is one way to construct modular forms, whatever those things are. And then what is the counting function for this particular example? It's a very hard question. There's a very brilliant German mathematician, Hacker. He found the answer. Actually, he did a whole lot more than this. So this is the general theta series, but I'm applying it now for E8. What are these counting numbers? He found that they're given as a sum of divisors. So I have to give, and what I'm saying is, what he is saying is quite a bit. We want all the counting numbers for every L in this infinite series. They're given by positive divisors of L raised to the 3rd power multiplied by 240. So we can, if we use this notation, go from the upper half plane to a point in the puncture plane, Q. This is a little dictionary. You can express things in terms of tau or Q. Because of Hecker's theorem, we have an explicit series for E8. And you need that for string theory, for example. One of the few examples you can do that. We can do it for general so-called holomorphic Eisenstein theory, but in general Fourier coefficients, automorphic forms are just completely unknown. The asymptotics are known, but not the explicit formulas. So I'd like to relate this theta series to some well-known, well, actually go back to Klein and Dedekind. the third part of the outline was to do this, to spell out this connection with this theta series to the classical Vatican decline invariant. So first of all, we defined the series that Jacobi defined back in 1829. There was another one, but we won't need it. These three Jacobi series here. Again, tau is always in the upper plane. Then, it's a very beautiful formula involving the number 8 again. The theta series is related to the Jacobi series by this amazing formula. We'll use that formula in a minute. We go first back to the Klein invariant. It's defined this way in terms of the, we call this the J invariant, or the Klein invariant. It's defined as powers of the Jacobi theta series. Take the 8 powers here. And just as the theta series for E8 had this modular property, you see it here also for J. That is, J of tau is the same as J is invariant under the action of SL2Z on the upper half plane, linear fractional action. By the way, this was studied by Vatican and Klein just a year apart. So here's the modular property for the theta function. There you have a 4th power. Here you have a 0 power. That's why we just called it invariant. It is stronger than modularity. Then, if I use the formula I had on the preceding page, I can express the J invariant this way, again for 8, the number 8 plays a crucial role. Now, I wrote a little book on all this stuff, application of all these theta series and modular functions, physics and the like.
Is this the same J invariant that you have for elliptic curves? Or
Yes.
Tau, okay, so
It's the same, yeah. You have to be a little bit careful with the normalization. There's something like a 1728 that comes in.
Sure.
So it is the same, yeah.
Which makes sense with tau for the lattice that you're generating.
That is correct. That is correct. So the purpose of the lecture is just to show the proliferation of 8 in a very beautiful way with some of these formulas. I'll make a little sad detour very briefly to the nearby zoo. So we know atoms consist of electrons. Here's the central nucleus that consists of what are called protons and neutrons. And swirling around this nucleus in certain orbits are electrons. That's what this picture shows. And that was a basic picture that we had in high school, but later we found out that, before I say that, so here's a typical example of the lithium atom with 3 protons and 4 neutrons to make the nucleus, excuse me. And then you need these electrons. These are negatively charged to keep the stability with these protons. If you have 3 protons, you will have 3 electrons. You don't care about the neutrons because they're neutral with regard to electric charge. The more complicated picture after high school is that the protons and the neutrons themselves are not indivisible, but they consist of what are called quarks. So if I go to the helium atom with 2 electrons, this one and this one, 2 protons, 2 neutrons, then each of these 2 protons consists of 3 further elementary particles called quarks. And so do the neutrons, that's the picture. Then one additional particle that will glue these together to keep the atom from disintegrating, they're called gluons. And they turn out to be 8 types of gluons. This has to do with, I'll say later, it has to do with SU3. That's the 3-dimensional Lie group. The quarks are even more complicated because, well, I won't get into that. But even the gluons, they are complicated because they come in different colors and also anticolors. You can have red, you can have green, you can also have anti-green. The thing is, when Dirac wrote down his equation for electron, he realized that to every particle there's an antiparticle. And he said, something's wrong here. This can't be right. It can't be right. Because it predicted an antiparticle. Nobody had ever heard of antiparticles. He checked his equations again, and they were right mathematically. So he said, I have to live with it. And sure enough, he was vindicated. So there's a general classification of, again, I'll be very brief about this, of elementary particles. They could be hadrons, that is, they could be sensitive to the so-called strong force, or they could be insensitive, they could care less. They're called leptons. So you can have protons, neutrons, again, antiparticles, that's an antiproton. You can have particles of integral spin. You can have fermions with half spin or 3 half or 5 half spins. But these are called bosons. The hadrons, that's particles that are sensitive to the strong force. They include electrons, big electrons with mass 300 times the electron, or even a tau particle with mass 3,600 times that of the electron, was discovered in 1975. Or zero mass, like neutrinos that fill up this room. They're leptons. Now back in 2007, there was a man named Anthony Lisi, who's a physicist. We call him a surfer dude. He called himself a surfer dude, unemployed, but he decided that there should be a theory of elementary particles based upon E8. And it was somewhat amazing. He looked at the 226 bosons. Again, these are examples of your hadrons. And he predicted 22 more new particles. And that sum would be 248, which is really the dimension of this Lie group called E8. This is a stroke of genius, but it's not quite true. The physicists have really attacked him, but I don't think you can attack the genius that he has. It's the work in progress, that's one way of looking at it. More work needs to be done, but it's still kind of very bold prediction. I'll say a little bit more about that at the end of the lecture. So I have 2 more slides on this, and then I'll go back to the mathematics. In addition to E8, there's another 8-dimensional space that I mentioned a minute ago. It's called SU3, the set of 3 by 3 unitary matrices with determinant equal to +1. I'm looking at a little SU3, that's the algebra, that so-called Lie group. And that space corresponds to these 8 types of gluons that I mentioned a minute ago. This is the definition of SU3. These are matrices that look this way. You have 1, 2, 3, 4, 5. You have 8, 9 real numbers. But you want the trace to be 0, so that gives you, that takes away a degree of freedom. So instead of having 9 numbers, you've got 8 dimensional space here. That's what SU3 is. And also the quarks and the antiquarks are associated with this group SU3, 8-dimensional space. The last slide on this is deals with a pivotal role that, again, that the number 8 plays. If you take the hadrons, remember how the hadrons and the leptons, with that further subdivision of the hadrons, you have what are called baryons and mesons. I won't say much about the mesons. But the baryons are the protons, and there's some strange particles. They're called lambda, sigma, cascade. And 1960 period, Murray Gell-Mann and Yuval Ne'eman independently, they figured out that if you arrange these particles this way, you would get a what's called an octagon. 1, 2, 3, 4, 5, 6, and 2 other particles. These turned out to be related to so-called weight diagrams or root diagrams for this the algebra. The weight for the Cartan subalgebra is 2-dimensional. That corresponds to these 2 particles here. The others correspond to 1-dimensional. We call them weight spaces in general, but it's the adjoint representation, so it's really the root space. So the burning question, have you heard a baryon today? The smiley face person. I'll go back to earlier formulas. We're repeating the definition of the J invariant. And in Hackett's theorem, we have explicit expansion of this theta function because Hacker computed all the counting numbers quite explicitly. It's even easier to do that for the so-called J invariant. It takes some proof, obviously. Here, just repeat what we did, what was done by Hacker for the A theta series. Again, the dictionary is tau goes to Q this way. And then there's expansion for the J, certainly requires proof, but it begins to look this way. We reminded us that the J function is given in terms of the Jacobi, the 3 Jacobi classical theta functions at the bottom of the page here. I was talking with Caleb. He anticipated something that I could say now. I'm just rewriting the J expansion. And we make this particular choice. So far, tau has been any element in the upper half plane. But let's make this very specific choice for tau. 1 plus the square root 163 times I divided by 2. That's in the upper half plane. And I call this tau sub r after Nugent. If you plug this value into J here, it's a very remarkable fact that you get an integrality condition. This turns out to be an integer. But first of all, it's supposed to be a complex number. Then it turns out to be real. That would be a miracle in its own right. But now it's also an integer, so it's a very remarkable fact. And then this particular number is called Newton's constant. It's not divisible by 8, it's not an integer, but it's nearly divisible by 8 if you write it out. I've got all these 9s here. Then you can turn out the factor this way. So it's nearly divisible by 8. Now it's time to add to that. There are lots of numbers that are nearly integers. If you take the golden ratio, for example, you have to take the square root of 5 plus 1 over 2, raise it to a large power. It's nearly an integer. It may not be divisible by 8, though. There's a whole subject. You can go to the Google and just Google near integers. A lot of work on that. And by the way, you can also think of this expression as a little calculus expression. Say you integrate something, you have an upper limit and a lower limit. You subtract 24, you get. So this is a polynomial evaluation of this number. So that's not obvious. So I want to make some final remarks as I close out. I have a paper where you look at so-called holomorphic conformal field theory. They have what's called a central charge, and you'd like that to be divisible by 8. The simplest case is 24. And such a theory was constructed by Jim Mikowski and a couple other people. Witten wants to claim that you can construct all these theories for general central charge divisible by 8. But that's not true because one of the physicists showed that they lose monster symmetry. The monster group, the largest sporadic simple group, has about 10 to the 48 elements in it, something like that. So you might be able to do it, but you certainly will lose monster symmetry. The monster group is somewhat this secret symmetry group of three-dimensional quantum gravity. But for this, we need not only just the J invariant, but we also need this cube root. And it turns out, this work goes way back to the early part of the 20th century. Moraine and Desjardins computed they didn't do what Hecker did. They used computers to get these numbers up to n equal 160. I'll just show you what it looks like. So here's the first number. Get about the 1, but 248. So in the next slide, we'll look at these three numbers, the first three numbers just appear. But what are the rest of these numbers if I take n equal 4, 5, and up to 160? But they gave a table based on the computer programming. Can you see that? So you know the first three numbers, I just showed you those. So put the zero to get one, now you know these three. And then this is the rest of the numbers down to number 40. The only reason I'm showing this is to show that it can be done. And these numbers pretty quickly. Once you get around here, you've outgrown the national debt, 18 trillion. So it can be done. I'll skip the third one and the last one, 160. Just to give you the magnitude of the numbers. Oh, excuse me. So this is the 160th coefficient. The order of magnitude is around 1 trillion times 1 trillion times 1 trillion.
Is that a 27 million?
Question?
Is that a 27 million?
That's 77.
77.
77 trillion times 1 trillion times 1 trillion. So with that slide that we have with the particle zoo, with the geometry of the SU3 is representation theory, because I didn't really go into the weight spaces and so forth. I did mention the vowel group. There's a vowel group involved as well. But it turns out this to be the symmetric group on 8 letters. There are very deep arithmetic and geometric ties that reign in the majestic world of E8. And a couple thousand years ago, remember that Plato said, the God ever geometrizes. Carl Jacobi said that God ever arithmetizes. This is a beautiful link here. And then my MIT postdoc, Professor Costin, said that E8 is the most magnificent object in all of mathematics. It's like a diamond with thousands of facets. It is easy to arrive at the feeling that a final understanding of the universe must somehow involve E8. And he bases that statement on string theory, but still there's a lot of holes in string theory, mainly the experimental evidence for string theory. But there's something there I want to think. And I end the letters with kudos to this super dude, Lisa, that I mentioned earlier. The vision is not completed, but there's something about that vision that just I find very fascinating, very exciting. Thank you very much.
Anyone have any questions?
You may have mentioned it earlier, but what was Minkowski looking at when he proved that theorem that you had at the beginning of the talk? What sort of motivated that?
He was studying so-called geometry of numbers. He was not so much looking at the particular problem of writing the number as a sum of squares, but there's a book, I must admit I haven't read it, entitled The Geometry of Numbers. And it does involve a lot of n-dimensional geometry with different figures and so forth. That was his basic motivation.
Okay.
So is there a specific threshold you need to be a near integer? I'm just curious, like what constitutes a near integer?
Well, if you have a integer with enough, and a decimal point with enough nines about it, behind it, I think that would be probably good.
So there's no like technical definition, it's not like you need like 10
No,
nines or something?
it's empirical.
Yeah, alright.
What I didn't show you, I mentioned, reminded you, he has a crazy formula for 1 over pi in terms of a very, very complicated infinite series. And that infinite series involves a lot of numbers that if you take the sum of all those numbers, you get an extremely large number. That number turns out to be divisible by 8. There's no reason in the world why that should be true. But I didn't mention it, I didn't put that in the slide, but again, probably if you would Google near divisibility by 8, there's even a criteria. If you have a great big long number, look at the last 3 numbers as 10th, 100 and 1,000th place. If that's divisible by 8, then the whole number, no matter how large it is, that's divisible by 8. And then he gives some examples of numbers that are nearly integers. And of course, I mentioned the golden ratio to a large power, that caught my attention.
Let's thank our speaker again.
Thank you very much.